before we get started, do we have any general question on the class style, administration, access to the recording, etc.? No? Okay, ready to get started. So in our last lecture, we went over ideal gas law, meaning that we started from the two experimentally derived law, like Boyle's law and Charles' law. We will manage to derive our ideal gas law, or PV equals nRT. Now, like the ideal gas law or the van der Waals gas law that we saw, they are all equations of state. Right, so when we talk about an equation of state, what we are saying is that these are the fundamental equations describing the relationship between properties like the molar volume, pressure, and temperature. These are only equations of state for homogeneous systems. Now, for heterogeneous systems, remember, for heterogeneous systems, you have different homogeneous parts or phases. Now, those phases can also be described using the equation of state. Typically, in this class, we will focus on the homogeneous fixed component system, meaning there's no material exchange or chemical reactions taking place. And then we can simplify our system into three different variables. We have pressure, temperature, and also molar volume. So remember, the definition of molar volume is volume divided by number of moles. Now, like our ideal gas law, these equations of state are experimentally determined. So now the question becomes, how many experiments do we really need in order to obtain or have a way to solve for these equations of state? If you think about it, we have three different variables, right? So we have the molar volume, pressure, and temperature. They're dependent of each other. So if you think about it, we have a total of 6 partial derivatives you can come up with, right? We do the partial derivatives in a pairwise, keeping the third variable as a constant. Like, for example, we can have an isothermal process. So when we say isothermal process, in thermodynamics, it means we're keeping the temperature as a constant and focusing on the relationship between pressure and volume. So the pair of partial derivative we can come up with is a partial derivative of molar volume with respect to pressure at constant temperature, or you have partial derivative of pressure over molar volume at constant temperature. But using our calculus, basic calculus, you know that these two are connected, right? So the partial derivative of any function z and x at constant y will equal to 1 over partial derivative of x over z at constant y. Now we're just replacing x, y, z with p, v, or t. Right, so in this case, we see that these two are a pair of partial derivatives, but they are interconnected. It's also very straightforward to understand, right? So in this case, if we have a PV diagram at constant temperature, it doesn't matter if I put the pressure on the y-axis or the x-axis. We're describing effectively the same relationship between pressure and volume at the same temperature. So these two are interconnected. Likewise, the same kind of rule applies to isobaric and isochoric processes, right? So like isothermal processes, we're saying these are processes taking place at constant temperature. Or we can keep the pressure as a constant, and that's called isobaric process. Right, so keeping pressure as a constant, we can derive relationship between temperature and volume at constant pressure. So these two are two sets of partial derivatives that are connected to each other. The same applies to isochorous process. So that means we're having constant molar volume. We're keeping the volume the same, and then making a relationship between temperature and pressure. So remember, we start from 3 different variables with a total of 6 partial derivatives. Now, just using the very simple mathematical relationship, we're able to reduce that 6 partial derivatives into 3. We don't have to do 6 experiments. Now, maybe we only have to do 3. But if you think about it, we only use 2 experiments to derive for our ideal gas law. Now, we have one more link to further reduce the, well, I don't want to say degree of freedom, but to further reduce the number of experiments we need to perform in order to obtain the equation of state. So the relationship we're going to use is the cyclic chain rule. In the cyclic chain rule, we have, well, some kind of differential dx over dy at constant z times dy over dz at constant x times dz over dx at constant y equals to -1. That's just calculus. But if you think about using the 3 partial derivatives we get in isothermal, isobaric, and isochorus processes and use our cyclic chain rule, obviously we have one more relationship to link these 3 partial derivatives together. So we can do one less experiment, right? So how exactly is that? What exactly does it mean? So if we put in our pressure, molar volume, and temperature, we get it to partial derivative of pressure over Vm at constant T times partial derivative of Vm over T at constant P times partial derivative of T over P at constant Vm. That equals to -1. All right, or the other way to put it, let's just focusing on these 2 terms with volume in there, because it's easier for us to measure how does the volume of a gas change with respect to temperature or pressure. We can write this one out. We're just moving this term to the right-hand side. What we have is, well, partial derivative of P over T at constant Vm. So basically moving that to the right-hand side and taking the negative back to the left. This equals to negative partial derivative of P over Vm at constant T times partial derivative of Vm over T at constant P. And, well, it's not too straightforward to measure P over Vm, but it's easy to measure Vm over P. So we're going to use our relationship, which is, well, dz over dx at constant y equals to 1 over dx over dz at constant y again. And this equation becomes negative. On the top, we have our dvm over dt at constant p, and on the bottom we have our dvm over dp at constant t. Right, so it tells us these are the 2 partial derivatives we need to experimentally measure. That's everything we need in order to solve for an equation of state. And if you think about what we did with the ideal gas law, we're actually doing these experiments without knowing everything about it. Like the Boyle's law, right? So the Boyle's law is done at isothermal process or a same temperature. So that's the bottom one. At isothermal, that tells us like PV equals to some constant K. It tells us the relationship between pressure and volume at constant temperature. Likewise, the Charles law, that's V equals to A1 plus A2 theta. So that theta is degrees Celsius. And this one is done in the isobaric process. That's the same idea about temperature, right? So this one is done at isobaric processes or the constant P, and the Boyle's law is the constant T version, right? So effectively, we only need 2 different experiments in order to determine what is the equation of state. So take it one more step. Scientists decide, okay, so let's just call these 2 partial derivatives something to measure. So they become a property of, or an equation or a relationship that we care about of any specific equation of state. So these 2, now we have the definition of the 2 terms. The first one is called thermal expansivity, or the cubic expansion coefficient. So alpha, which is a function of temperature and pressure, tells you how does the volume of a homogeneous substance change with respect to temperature at constant P. Right, so that's an isobaric measurement. And at the same time, we define chi or kappa, so that's the isothermal compressibility. So chi, which is a function of temperature and pressure, so that is defined as negative 1 over Vm, and describes a partial derivative of volume over pressure at constant T. It looks very complicated. It can be complicated too, but for ideal gas, let's just look out. What exactly is the unit or the dimensionality of my alpha and kappa? Now again, we have our ideal gas as P Vm equals to RT. Now Vm is our molar volume. You can also rewrite this equation as 1 over V, dV over dt at constant P and N. That's the same idea. Now, can we quickly solve for alpha and kappa for ideal gas just to get an idea about what's the unit of these coefficients? Or we can write Vm as RT over P. So this should be quite straightforward. Alpha equals to 1 over Vm, or we know that Vm equals RT over P, so that is P over RT, times the partial derivative of Vm over T. Now that just equals to R over P. My P and P cancel out, R and R cancel out. So the unit of my alpha is the same as 1 over T, or K minus 1. All right, so this is a kind of question that, for example, if I just ask you, what is the unit of kappa? And you look at this equation, you'll be like, I don't know. I have no idea what's the unit of a partial derivative. But the idea here is it doesn't matter what equation of state we use when we're solving for the unit or dimensionality of these coefficients. Well, you can use our simplistic equation of state and just do the quick calculus here. Likewise, let's solve for the unit of kappa or chi. So chi here equals to negative 1 over Vm, so that's P over RT again, and times the partial derivative of Vm over P. Now P is on the bottom, so we have RT out, and the negative 1 over P squared. Again, lots of things cancel out. Your RT cancel out. P and the P squared cancel out. And the negative and negative cancel out. Your kappa equals to 1 over P for ideal gases, or the unit is like bar minus 1. Or torr minus 1, ATM minus 1. As long as the unit for pressure, that's the same. All right. So everything looks very straightforward, but I do want to show you, taking you one more step beyond ideal gas, just for now, to show like what's the max amount of math we will be using in the rest of this quarter. So whatever we are doing in the next derivation, that's the amount of math we need for this class. We won't go even more complicated than that. I don't expect you to do that by hand anymore. But the next one will be a demonstration in how complicated math can be in this class. And we can look at it together. So the idea here is if we go beyond ideal gas, let's focusing on the van der Waals gas, right? So P equals to A over Vm squared tells you there's attractive forces between your particles in the van der Waals gas at certain distances, times Vm minus B tells that in van der Waals gas, the gas will have a volume. It's like a solid ball, equals to RT. So that's the equation of state of a van der Waals gas. Again, it's like ideal gas. It describes the relationship of the change in molar volume, temperature, and pressure. Now, can you solve for the thermal expansivity, which is alpha equals to 1 over Vm times partial derivative of Vm over T at constant P. All right. So this one, we have three different ways to solve it. The first and the most complicated one is to try to solve this quadratic equation and get an expression of Vm in pressure and temperature. That's the most straightforward but too complicated for us to solve. Instead, we can use multiple calculus strategies to approach this problem. Now, the first strategy you could use is, again, using the cyclic chain rule. So remember the cyclic chain rule, we're talking about the difference or the relationship of different partial derivatives. Right, so in this case, it is hard for us to solve for Vm as a function of T and P. But it is relatively straightforward for us to solve for a function of T as a, to solve for T as a function of Vm and P, or to solve for P as a function of Vm and T. Right, so it's easier to solve the partial derivative of P over Vm at constant T, or partial derivative of T over Vm and constant P. So I demonstrated that in my 9 a.m. session. It's also in my recording and also in the annotated note. So you can try this yourself. But I want to work with you on our second approach, which is again using calculus. But now the key is to say like dxy equals to x dy plus y dx. Like these are all calculus equations that we see in lecture 1. Like when we go through it really fast, you'll be like, yeah, I know this. But this is how we actually use it in solving thermodynamic problems. So we'll do this together. If you have a piece of paper, we can work on it together. Or if you want to just look at the board, that's also fine. Again, you don't have to write down everything. I have a detailed walkthrough on the annotated notes. So just pay attention and try ask any questions that confuses you. Okay, I'll leave it here, and we will be using the second approach here. They will give you the same answer, so that's the nice thing about this class. You can always solve the problem in a different way, and then check your answer later on. Okay, let's get started. So, the van der Waals equation we have is P plus A over Vm times Vm minus B equals to RT. So do people in the back can see my handwriting? Okay. Now the first step we're going to do is taking derivative on both ends with respect to dt. And the reason we're doing it is, well, that's what we want, right? We want a partial derivative of volume over t, but let's just do it on both ends with respect to t. So that's set up to be d over dt of this p plus a over vm times vm minus b equals to d over dt RT. So some of the things are straightforward, like this one we know how to solve it. But let's just look at this one. Let's call this first term as x and this term as y. So my x equals to p plus a over bm, and my y equals to bm minus b, right? And then what we're doing is, in this case, solving for dx over dbm. So dx over dbm, taking together to what we want in dvm over dt. So that's why we have the dvm on the bottom here. We want the x to be canceled out, remember that. So in this case, so setting up for dx over dvm, this one p goes away, so this becomes negative 2a over bm third. Or we can write dx equals to 2a over bm third dbm. That's the dx part. On the dy part, we're doing the same. So dy over dbm, that equals to, well, just 1. Very straightforward. And my dy equals to dbm. Right. And, well, that's what we have. The dxy equals to x dy times y dx. dxy equals to x dy plus y dx. And now it's just plugging numbers. We know what x is, we know what dx is, we know what y is, we know what dy is. We're just effectively plugging numbers into this original equation. And what do we have? So what we have is the following. Let's do x, so that's p plus a over bm times dy. Let's see dvm. Right, so remember in the before we have like d over dt. No, okay, so the d is already taken care of because we're doing the dxy. So this is over, everything is over dt. All right, so that's the x dy term plus the y dx term. So y bm minus b dx term. Let's see, I'm missing a negative here. Yes.
Shouldn't it be a over bm squared?
Yes, good catch. Okay, yeah, this one is correct. I just forgot that. And then we have this dx term here, which is a negative 2a over bm third. And this entire thing dvm. And on the right-hand side, it's just r. Right. So now, obviously, we got our dvm over dt. That's what we want in this equation. So it's just a shortcut to give us a way to solve for the derivative dvm over dt. Or, later on, you can write it out as the left one. bm minus b, and, well, we're assuming dvm over dt at constant pressure, or in reality, we want to write it as a partial derivative. Minus 2a over bm third times the bm minus b, and this dvm over dt term. all right? And then just moving terms around, we got what we want. We got this partial derivative and expressions in front and outside of it. So you can move the term yourself, and the expression we're gonna get, the partial derivative of Vm over dt at constant p equals to this complicated equation, r Vm third, wait, this one should be second. Vm, wait, sorry, yes. Minus b rt Vm third minus 2a times Vm minus b squared. So you can check it yourself. But this is the calculus part is not hard. The hard part is moving terms around and make sure you don't make any mistakes. And since alpha equals to 1 over Vm times the partial derivative of Vm over t at constant p, we're just canceling out one of the Vm on the top. We got r Vm second times Vm minus b, and the bottom stayed the same. Rt Vm third minus 2a times Vm minus b squared. So I want to ask you a quick question here. Now, what is the unit of this alpha here? Doing the same kind of analysis, what is the unit of our alpha here? It's the same logic. Now on the top, Vm minus b tells you Vm and b must have the same dimension. So on the top, we have r times about Vm to the third. I'm not saying they're the same equation, I'm saying they have the same dimension on the top. On the bottom, it's the same. Now these two are minus to each other. So we don't care about the actual unit here because they must have the same unit, so we can plus and minus them together. Right, so what we're doing on the bottom have the unit of RT Vm third. So that's the dimensionality we're looking at on the bottom. Right, so some of them cancel out, these cancel out, R cancel out, so the dimensionality of my alpha, even if it's way more complicated than our ideal gas law, the dimensionality is still 1 over t, or the unit is k minus 1. So this is a very nice sanity check after your derivation, because we're looking at alpha. It's just a different equation of state. It will have the same dimensionality. So this will have the same dimensionality as our ideal gas. Or you can imagine some random other equation of state. You will end up having alpha being having the same dimensionality as what you see before. All right. How are we feeling about the math part? I mean, it's lots of equations and looks very complicated, but effectively, the calculus we're using is just a dxy equals to x dy plus y dx. We're just using different symbols to make them look very complicated. But that's about as complicated as we're gonna get in this class, just to give you an idea about how much math you need. Again, we're not using very complicated math. It's just the nature of these equations makes them look horrible. Any questions? Yes?
Sorry, could you explain one more time how you got from that bottom equation?
This one to here. Well, this one is having the dVm over dt, right? But in this whole process, we actually have the assumption that pressure is a constant. And that's why I'm just rewriting that into the actual physical meaning of those equations. Because in this whole process, we're assuming pressure is a constant. So we can do all these derivatives. Or if we want to go way more like correct in this part, I shouldn't do normal derivative. I should put like the partial derivative of dx over dvm at constant pressure. It's just gonna make it like longer, that's all. Yeah, again, I'm not a mathematician, so it's not the most accurate or the flawless derivative I want to show you, but that's how we solve this problem. Okay, any questions before we move on to lecture 3? All right, sounds good. And again, if you got the time, I highly recommend you try it using the cyclic chain rule and check your answer. We'll get the same answer. Okay, let's see. Lecture 3. And now we're moving on to chapter 2. So we have finished chapter 1. And I hope you are feeling okay with your chapter 1. Now we're moving to chapter 2. In chapter 2, we're focusing on the first law of thermodynamics, which relates energy, which tells you how does energy perform, or what is the law of thermodynamics taking care of internal energy. But before we talk about the laws of thermodynamics, again, we want to define or make sure you understand every term we're using in that first law of thermodynamics. So this lecture will again be more of a preparation lecture, so you have an idea or the background knowledge of basically classical mechanics and PV work and also heat. So today we'll hopefully finish the first 2 topics. We'll leave heat for our next Monday's lecture. Getting started, classical mechanics. Right, so classical mechanics is something you learned in physics. So think about this, instead of a math review, it's more like a physics review. When we're talking about classical mechanics, like thermodynamics, we take care of the macroscopic body's movement. Again, macroscopic bodies are something like you can actually touch. It's not like too small. Something like an electron would consider a non-macroscopic object, and you cannot use Newton's law to describe the movement of an electron, and you need quantum mechanics. Or for something that's moving super fast, right, almost at the speed of light, we can no longer use Newton's law. We need to use the relativistic mechanics. But for this class, we'll stay in the nice old days of classical mechanics. So we use classical mechanics to describe the movement of these macroscopic objects. So some review on the Newton's law. We have several relationships that are fundamental in classical mechanics. We have force. So the force is a vector which equals to mass times acceleration, where acceleration is defined as the second derivative of that movement along one direction over time, while velocity is the first derivative of that movement over time in that direction of interest. And on top of force, velocity, and acceleration, we have work. So work, that's assuming it's one-dimensional. What it says is that a force F is acting on a body when the body undergoes an infinitesimal display of dx in the direction of x. That's what this means. It tells you the change, the differential of work equals to fx dx. Now, this fx may be a constant and may be a function of x as well. So that's just a general picture. And we will talk about in the classical mechanics, we have 2 different types of mechanical energy that are conserved. So in the mechanical energy parts, work is related to our kinetic energy. Or the other way to put it is the work done on the particle by the force acting on it equals the change in kinetic energy of the particle. All right. So we'll do a very quick derivation here. This should be a review for you that you did in the physics class. But if we think about, let's having F as the force acting on that particle. And now just focusing on direction x only. So in my lecture note, you have the 4 derivation with x, y, and z, right? Let's just focusing on one direction movement. Now your work will equal to the integral of fx dx in one dimensional. And what we know is that in Newton's law, we know that Fx equals to the force along the x-axis equals to mass times acceleration along the x direction. And the acceleration is defined as the derivative of velocity along the x direction over time. And since we know that Vx, or the velocity, equals to dx over dt, we can further write this relationship as m dx, dvx over dx, and then dx dt. Right, we're just adding a random, we're just adding a dx in here that will get canceled out in this derivative. But since we have the relationship of Vx equals to dx over dt, we can rewrite this as mVx dVx dx. Right, so that's our force. So putting this expression of fx into our work derivative, we got w equals to mVx dVx dx times dx. Now this dx got canceled out. We got our work equals to mVx dVx. Right, and solving for the integral, we got it to be 1/2 m Vx2 square minus Vx1 square. Right, because this integral is taken between V1 to V2. Or the other way to put it is the kinetic energy of a particle is defined as k, or like 1/2 mv squared, then our work is defined as k2 minus k1. Right, so again, back to our original definition of the work energy theorem, what we are saying is that the work done on the particle, so our work done on the particle is the same as the change in kinetic energy of the particle. So keep this in mind. We will come back to it very soon, talking about why it is important to remember work is a property that's only defined by the differences or the change in kinetic energy. It has the same, yes?
Should we know these derivations for the exam?
Well, yes and no. I'm not going to ask you to derive the work energy theorem, but some part of it might appear in the exam. Yeah, so later on when the exam time approaches, I'll give you a more complete document in what we expect you to know. But this part might, because this is just a simple derivation. Okay, next up. The other part of the mechanical energy is the potential energy. So the potential energy is something you probably already know. Unfortunately, it's also abbreviated as V. It's the same as volume, but this one is potential energy as a function of x, y, and z in different directions. So for each direction, you have the partial derivative of V over x at constant y, z equals to negative fx. So that's just the derivative of the potential energy in that certain direction is equals to the negative of the force exerted in that direction. All right. And then at the end of the classical mechanical part, we want to refresh your memory on the conservation of mechanical energy. Right? So the total mechanical energy equals to kinetic energy plus potential energy. And if we only have conservative forces, typically normal forces are conservative, your mechanical energy will remain constant. I left a sample problem in below here, which is, well, problem like 2.6 that didn't show up for some reason. So that's just a sample question in classical mechanics and converting unit of energy. All right, and now let's move back to work. Again, we went over the PV work, and I just want to add one more thing about the PV work. So in this case, we're talking about a reversible PV work, or typically in thermodynamics, we focus on reversible work. So in this case, let's say a reversible system is defined as it is always infinitesimally close to equilibrium. And any infinitesimal change in conditions can restore both the system and surrounding to their initial state. So in our class, whenever we say a process is a very slow process, it pretty much tells us it is a reversible process. And in reversible cases, there are properties that we can only derive when it is reversible. We're focusing on reversible processes mostly in this class, unless otherwise specified. But if we're focusing on reversible PV work, we can take it one more step further to make it more useful for us. Because remember, we care about relationship between pressure, volume, and temperature, right? So in the original derivation or definition of pressure, we have dW equals to, let's say on x direction only, equals to Fx dx, right? But in thermodynamics, that Fx is less useful for us. We care about relationship of pressure, volume, and also temperature. So translating that into pressure and volume, we're thinking about a very simple, like one-dimensional system, where Fx and dx are pointing in the same direction. So we're doing positive work onto the system. The system can be anything that we care about, maybe a cylinder of ideal gas. And then when that force is exerting on there, we're doing it very slowly, so the volume of the system gradually decrease. So in the same process, we have Px, or the pressure of the system, is, or the pressure in that direction is defined as Fx over area, right? So pressure is equals to Fx over A. And we have dW equals to Pxa dx. Now, in this one-dimensional system, we have the volume equals to negative A dx. This negative comes because when we're exerting force on there, obviously the volume of the system shrink as x moving into the same direction as the force. And the final result we get is whenever we have this reversible movement, dW reversible equals to negative Px dV for closed system reversible. Or in this class, more often when we're looking at PV work, whenever we say PV work, we're referring to this kind of work. That's reversible PV work. We'll have the relationship as dW reversible equals to negative PdV for closed system reversible. Or if we take the integral on both ends, we got the work reversible equals to negative integral of P dV, where P is a function of V. All right, so in this class, we will be using these two equations very often. Now, going back to our original statement, when we say the work is a path-dependent function, or more specifically, it's a line integral, meaning that the work itself at any point. That's not being defined. Let's say we have something that, like my pencil in my hand. Now this doesn't have any work. The work is not a defined term. It only defines, say, if I'm moving my pencil from one point to the other. Work is only the property associated with this change of state, right? Any state itself doesn't have a work affiliated with it. What does it mean? It means that for us to get an idea about what the work is, we must know what is the path it's taking from one state to a different state. So let's imagine we have a PV work that's done in different ways. Now, a PV work diagram, typically we have a coordinate on the y-axis, you have the pressure, on the x-axis, you have the volume. Let's say we start from our initial point, P1, V1, and we end in our final point, P2, V2. I'm gonna copy paste this exact same diagram on the top and on the bottom. And thinking about doing the work in two different ways and having different work. Now, in the first situation, imagine we have an isochoric process followed by a isobaric process. So remember, isochoric tells us is constant volume. So we have a straight line going down, right? We're keeping the volume as a constant. So that's our first step. Second step, isobaric. So constant pressure. And that goes to our final spot. Now the work that's being done, remember our work reversible equals to negative PdV, or you take the integral on both ends to get the total work that's being done, right? So whenever you're taking the integral, it's pretty much asking you what's the area below the curve. Now that's the curve we created along the isobaric path. So that gives us the area below the curve to be something like this, right? Alternatively, if we do this process in a reversed fashion, we do it isobarically first at constant pressure, and then we do it in the isochoric fashion. And that goes down like this. Right, so now what we have under the curve is a much larger area below the curve, just because we're taking different paths going from state 1 to state 2. All right, so this is very important to keep in mind that work is a property associated with a process. We have to define the path in order to calculate the work that's being done from state 1 to state 2. All right, you could have a exotic pathway. Like for example, if we just go like something like this, it's the same idea, right? But the area below this curve will be way more complicated for us to calculate. Now, work is one of the line function we will be using. Next lecture, we'll go over another line function, which is heat. But taking work and heat together, we will be able to define thermodynamic state functions that we will be using. All right, so just keep in mind work, line function, path dependent. You need to know the path in order to calculate the work. All right, that's everything I got today. Well, good luck studying. Remember the deadlines, right? One at tonight for the syllabus quiz and one at Sunday night for your discussion worksheet. All right, good luck.